force of gravity. Because this is the radius, we will say that the force of gravity is an attractive force. Attractive force always is less than 0. So since the force of gravity is acting in this direction and the radius is in this direction, from that is the negative side, the negative sign. So the radius vector is in this direction, is the distance or the distance from here to where is the mass. This is what we call radius vector, where the particle is moving. And the force of gravity is in the opposite direction, from here the negative sign. Because it's in the direction of the radius, I have to put it, the magnitude is this. But if you want to get a vector in the direction of the radius, you remember that will be the unit vector in the direction of the radius, r. Which r, you know, that is the absolute value, I mean the radius as a vector over the absolute value of the radius. This is what we call unit vector in the direction of the radius. It's just to mark the direction, but the dimension is 1. So if you multiply anything by 1, but in that direction, will give you a vector in that direction. Okay, this is just the definition of gravitational force. The magnitude of that force, of course, will be G n, if we label the outer mass, the satellite, lowercase n, and the central body, capital N, over r squared. This is the magnitude. So it's the same n1, n2, that if we want to say the central body is capital M, and the satellite is lowercase n. And that's the magnitude. But that magnitude of the force is at any point. It's not just on the surface of the Earth, which was mg. It's anywhere. But because we know that this is moving with an acceleration, which is centripetal, since it's moving at constant speed, there is no tangential acceleration. It's only centripetal. So that centripetal acceleration is MAR. The centripetal acceleration, A radial, or centripetal. That A radial is what we call universal acceleration due to gravity, mg, the absolute value. Here will be mg, but g is negative. G. And this, because it's moving in a circular path, we learned before, very superficially, that the centripetal acceleration is equal to, or the centripetal force is equal to MAR, which is mv squared over r. Here I am using the term that the centripetal acceleration, AR, is v squared over r. This is basically, from here will come most of the definition, or most of the theory of gravitation from that statement. In other words, Fg is the force of attraction between two masses. Can be found in different ways. One, with this, which is the universal law of gravitation, found by Isaac Newton. G is a constant, found by Cavendish at MIT. M, the mass of the outer object, which is the satellite, orbiting the central body. If we have just two masses, you just multiply the product of the two masses and you divide by the distance between the two masses squared. This stands for distance between the two masses squared. mg, this is the mass of the satellite, time gravity, the acceleration that has the satellite. So the satellite moves with the centripetal acceleration, so with the velocity v, which is tangential, but the centripetal acceleration is in this direction, in the same direction as of Fg. That will be called mg. But again, it's not 9.8. Can be any gravity, depending on where is the object. The object not necessarily will be close to the surface of the Earth. Can be far from the surface of the Earth, and of course the gravity is not 9.8. The gravity can be any gravity. And that gravity will be called universal acceleration due to gravity. And then, because it's moving in a circular path, assuming that it's moving in a circular path as a model, and with constant speed, the force will be centripetal toward the center. And that centripetal force will be MAR. AR is the radial acceleration, which is V squared over R. So from that will come most of the formula of the first part of gravitation. The second part will be energy and angular momentum on the motion of the satellites. So let's start now talking about Fg, gravitational force. So as I said, Fg will be G in mass of the satellite, mass of the central body divided by R squared, the distance between the two masses squared. The first thing we need to know, if I give all this, it's very simple to find the force of gravity at a certain point. That will be just a simple calculation. Except that you will use scientific notation most of the time because the distances are very far, are very huge or big. So you need to use, for most of the time, scientific notation. G. G is called universal gravitational constant. Universal gravitational constant. The universal gravitational constant, G, was found by Cavendish, as I said before, at MIT, and is equal to 6.67 times 10 to the negative 11 Newton meter square over kilogram square. This is G, the universal gravitational constant. Doesn't have to deal with the acceleration due to gravity. Two different G. One is capital, one is lowercase. Good. Knowing that, now we can just find in two different ways. If I give the straight numbers, you just get the gravitational force. The gravitational force always is attractive, negative, means toward the center. If it's a repulsive force, the force has to be greater than zero. Normally, between two objects, a repulsive force has to be greater than zero. Attractive force has to be less than zero, negative. Good. Sometimes you can do a straight calculation for the force of gravity this way, or this way if I give the gravity at a certain location, or if I give the speed and the radius, you can find this way. The easier way, of course, you will use. Sometimes you will use proportion to get at a certain distance what will be the force of gravity or the new weight. So you know, for example, that on the surface of the Earth, if I give, for example, that the object on the surface of the Earth, this is the radius of the Earth, this is the mass of the Earth, this is the mass of the satellite. At the surface of the Earth, how do you calculate the weight of the object? mg, which is Fg, mg. So at this location, if we know, if we call this Fg, let's say for instance mg, or